Okay, our next presentation is from Dr. Toshi Sakamoto, I'm sorry. And his talk is entitled Nanoelectrochemical Switching for Storage, Reconfiguration, and Logic. Dr. Sakamoto is a principal engineer with the Low Power Electronics Association and Project, which is a research consortium in Japan. He received the Master's of Science degree in Electrical Engineering and the PhD in Electrical Engineering from Osaka University. He joined NEC Corporation in 1991, where he worked on nanoelectronic devices, such as hot electron transistors, single electron devices, and nanoelectromechanical devices. His current focus is on solid electrolyte devices that will be used in switching elements for programmable logic devices. Please join me in welcoming Dr. Sakamoto.
Thank you for kind introduction. Thank you very much. I'm from LEAP, which is the one of the project of TIA Tsukuba Innovation Arena. This was explained by Dr. Yokoyama. So today I'm going to give a talk about the non-volatile switch using the electrochemical reaction, which we call atom switch. And Professor Philip Wang gives us the nice introduction. So our memory categorized to the CV RAM, conducting bridge RAM. So I will follow these items. First, I will give you the switch technology, 2-terminal atom switch and 3-terminal atom switch. And I will discuss its application to programmable cell arrays. For this application, we use 2-terminal atom switch. Atom switch was developed by Dr. Terabe in National Institute of Material Science in Japan. The atom switch has a very small nanometer gap. This is the silver electrode coated with the silver sulfide, which is separated from the platinum electrode by a very small gap here. Silver sulfide is an ionic conductor. At this small gap, the silver bridge forms by an electrochemical reaction here. Right-hand side shows the conductance of the switch. By applying the voltage, the conductance is quantized in the unit of 2e squared over h. It's a quantum conductance. This shows the switching can be done by few atoms. But it's hard to handle the small air gap to utilize in a silicon LSI, so we use the conducting bridge in the solid. Here is the metal bridge formed in copper sulfide. Copper sulfide is also ionic conductor. This sulfide is sandwiched between the active electrode, copper, and inert electrode, here, the platinum. When the positive voltage applied to the copper ion migrate to the cathode, and the excess copper ion precipitate. And the copper bridge is formed, and the switch turns on here. We observed a large current of 1 milliamps through the copper bridge when the switch turns on. Inversely, when the negative voltage is applied, switch turns off. For turning off, the large current is also required. We also demonstrate a 3-terminal atom switch, which is composed of copper gate and source and drain. The copper gate is separated from the conducting path between the source and drain. When the positive voltage applied to copper bridge precipitate on the source and drain electrode here. Here show the drain current and gate current versus gate voltage. The drain current is biased at 10 millivolt to monitor the resistive state. When the bridge is formed, the current between source and drain increases. The switch turns on or off when the gate voltage is biased positively or negatively. Each on-off state persists without applying the voltages. The gate current is about 2 microamps. As you can see, the switching current can be significantly reduced compared to that in the two-terminal atom switch. This shows the cycling endurance. We control the biasing time by monitoring the on resistance so as to get the similar on resistance here. On resistance ratio is around 10:6. Considering the electroplating experiment, we can easily understand the operation principle. Here show the experiment by using the liquid electrolyte. The current switches are according to the biasing the voltage on copper. For on state, you can see the copper precipitation on platinum electrode. There is the another aspect in the drain current for on-off state. You can see the drain current is modulated by gate voltage here. This is caused by modulation in hole concentration in copper sulfide. Copper sulfide is a p-type semiconductor. When the copper ions migrate by applying the electric field, copper vacancy is formed and the hole is induced. This graph shows the hole mobility versus carrier concentration for different copper composition. The mobility is ranging from 1 to 10 squared centimeter over Vs. The hole concentration depends on the amount of copper. Here is the summary of properties of two-terminal or three-terminal non-volatile switch. On-off resistance ratio up to 10:6. Switching time is around 1 microsec here. For three-terminal device, the switching time is longer than for two-terminal switch. The advantage of three-terminal is the small switching current. The next step is the integration of the switch with CMOS. To embed the atom switch into the silicon LSI, we have used oxide as an ionic conductor instead of copper sulfide. Up to now, we have not confirmed the operation of three-terminal atom switch with oxide ionic conductor. In the following, I will focus on the two-terminal switch with oxide ionic conductor. This TEM image of atom switch. This is a TEM image of atom switch integrated in copper interconnect. The oxide ionic conductor is sandwiched between copper and ruthenium electrode. In order to reduce the process steps, copper interconnection is used for active electrode. We only need 2 additional masks to form atom switch. One mask is for opening the cover on the copper interconnect. The other mask is for etching the switch stack. This is the current voltage characteristics. The current is limited by MOSFET. The on conductance can be controlled by the set current. Set operation means the turn on. The reset operation means the turn off. The on conductance is proportional to the set current. So we can control the on resistance by this current. This shows the TEM image of switch before set and after set, before set and after set operation. You can see that after set operation, the dark region is observed between 2 electrodes. Element analysis shows that this region is composed of copper. The thickness of copper bridge is around 30 nanometer. The size depends on the on conductance. Here we intentionally form thick bridge for observation. Here we demonstrate the programmability of 32 by 32 crossbar switch. No select transistor is used in the crossbar switch to save the area. Select transistor are placed outside of crossbar switch. Here we use 64 select transistors. As shown in SEM image, atom switch placed on each cross point. To program the switch without select transistor, half-selected programming scheme is used. the programming voltage VP is applied to the target element, and unselected nodes are applied to half VP. The switch applied at 0 or half VP are not programmed, and the target element is programmed. For this programming scheme, the set voltage needs to distribute between half VP and VP. The left graph shows the measured set voltage distribution. The set voltage distribution between half VP and VP. The wide light margin of 1 volt is confirmed. The light graph shows the path resistance map and reprogrammability. The dark color means low on resistance, and light color represents a high on resistance. For example, the resistance of path of X1 through Y1 is low. The on-off resistance ratio is about 10 to 5. This connection pattern can be relatable. We also show the switching time. The probability to set or reset was evaluated with changing the amplitude for different pulse widths. Programming pulse was generated on the tip, and 1K bit is measured for each point. X-axis represents the amplitude of the voltage pulse. We change the pulse width from 5 milliseconds to 10 nanoseconds. We confirm the 10 nanosecond switching when the voltage is larger than 4 volt. Here, again, the summary of the switch properties. By using the oxide ionic conductor, we can successfully integrate two-terminal switch. And we confirm the large on-off resistance ratio and short pulse lighting. And let me move on to the next topic of application of atom switch.
May I interrupt?
Okay.
You call it an atom switch, which was a great name. Can you tell us how many atoms are actually being transferred?
It's hard to say. The size of atom is angstrom size, so the thickness of the bridge depends on the on conductance. We usually use the 1 kilo ohm range, so I think the thickness is a few nanometer. So that's, let's say, the tens of atoms. Okay, so here show the comparison of non-volatile memory in terms of technology maturity and memory state. As you know, NAND or NOR flash memory uses charge stored in floating gate. With scaling down the floating gate, the number of charge has become smaller. Below 10 nanometer, the resistive memory like PRAM and RERAM has a chance to replace the floating gate type memory. The active area can be reduced to less than 10 nanometer. PRAM and RERAM can be operated below 10 nanometer in principle. For our switch belongs to RERAM. Professor Philip Wong explained our memory type is the CVRAM. So the other type of RERAM uses oxide vacancy. And more importantly, this emerging memory can be formed in backend. It needs lower thermal budget. It has an importance for embedded memory application. The charge storage device needs a thick oxide. The thermal treatment may affect the CMOS properties. Here show the territory of memory in terms of cycling engines and on-off conductance ratio. You can see there is a trade-off between on-off ratio and cycling endurance. Here is the atom switch, which has the largest on-off on-off conductance ratio. RERAM with oxide vacancy also has an on-off conductance ratio. On the other hand, MRAM has a good cycling endurance. We believe the atom switch with high on-off conductance ratio is suitable to programmable switch in LSI. Here is the advantages for programmable switch, which are already explained. We have also reliability issues here. So reliability for on-state, reliability for off-state. Here is a requirement for programmable switch. For program logic application, we apply the pulse AC current. For off-state reliability, DC voltage stress is applied. The switch persists its on-off state for 10 years under these stress conditions. To evaluate the on-state reliability, we use the allowable current for 10 years durability. The allowable current is proportional to on conductance. And on conductance is also proportional to switching current. I mean reset or set current. The on-state reliability and switching current has a trade-off relationship. Here is the typical conditions. 37 microamp of allowable DC current requires switching current of 0.5 milliamps and on resistance of 400 ohm. AC current stress is more gentle than this DC current stress. The allowable voltage depends on the set voltage. To get good off state, we need larger voltage. We use the 3.5 volt for set voltage for 10 years retention. Okay. In the following, I would like to spend time to explain the programmable cell array with atom switch. Firstly, let me give an introduction of programmable cell arrays named FPGA. This slide explains the difference between ASIC and FPGA. Cell-based ASIC has been widely used for SoC platform, as you know. Here is a schematic of FPGA, which is composed of logic cells, interconnections, and switches to program these elements. FPGA does not need application-specific photomask. This slide shows the advantages and disadvantages of FPGA. The advantage of FPGA are short time to market and low development cost. Here is the FPGA sales by Altera and Xilinx. The sales has been rapidly increases. This rapid increase mainly caused from the increasing development cost in ASIC for advanced technology node. Despite of these advantages, FPGA has several issues listed here. First one is a large chip size and signal delay and increase in dynamic power. FPGA also suffers from the increasing the static power or variability in SRAM. The performance gap between SRAM-based FPGA is widely known. Here shows the performance gap between FPGA and ASIC, which is estimated by Professor Jonathan Lowe's group in Toronto University. The area gap is 30 to 18 for nanometer node. Delay gap is 3 to 4, and dynamic power 14. You can understand the area gap by considering the area of functional logic block in a chip. In the left, here is the schematic of FPGA again. The FPGA is composed of logic cell and hard IP core. In the program logic, the functional block only takes 3.4%. The rest of area is occupied by programmable connections. The area of functional block in FPGA corresponds to the area of ASIC. The average area ratio is around 30. Here shows the static power comparison of SRAM type low power FPGA with flash type FPGA. The difference in the static power is more than 1,000, since the flash memory stores the configuration data without power consumption. SRAM consumes the static power. So non-volatility is very important. So to narrow the performance gap, we need to reduce the area of programmable connections, which is occupied 96% of programmable logic. We also need a non-volatility to store the data without power consumption. The atom switch has these two features and enables to narrow the gap. This will be done by replacing the programmable connection with atom switch. Here shows our concept of compact switch over the logic. The left figure illustrates the conventional FPGA again. Right-hand side shows our proposal. Non-volatile resistive switch is stacked on the CMOS logic plane. Stacking also reduces the area, and the non-volatility enables lower static power. To compare the area, the programmable cell arrays based on CMOS switch is prepared. This is the die photograph of test chip fabricated by using the 90 nanometer node process. This slide shows the programmable cell featuring atom switch. 350,000 atom switches are integrated. You can see the significant area benefit. 72 chip area reduction can be realized. Both chips have the same architecture, including 32 by 32 programmable cells, configuration drivers, and I/O buffers. Here show the logic cell, which has 354 switches in metal 4 and metal 5. These results were given by Dr. Miyamura of NEC. Here shows the measured power consumption. This graph shows the power consumption versus operational frequency. Static power is smaller than the reference chip, and the dynamic power is evaluated from the slope of the plot. Compared with reference chip, atom switch-based chip shows 70% reduction in dynamic power. This reduction is originated from the reduced parasitic capacitance of interconnect and switch here. The capacitance of the switch is estimated to be 0.1 femtofarad, which is 1/10 of that of transistors. Okay, before conclusions, let me introduce our research consortium. Our objective of LEAP is ultra-low voltage device for low-carbon society. Our research consortium has several groups to develop the back-end devices. Here are research items of LEAP, which include MRAM, PRAM, and atom switch. And also we have a fully depleted FET, which is not BEOL device, but it's contributed to decrease the operation voltage and power consumption. And we share the wafer to reduce the development cost. Here is a summary of my presentation. Thank you for your kind attention.
Thank you, Dr. Sakamoto. Do we have any questions from the audience?
Oh, sorry.
This presentation is very fascinating to me.
Thank you very much.
And you showed a significant power reduction in FPGAs, which was very interesting. But I looked at the voltage requirement, and it seems like you still need a fairly high voltage requirement, maybe 2 or 3 volts. And I think it should be possible to reduce that because you are doing electroplating. Now, my understanding of electrochemistry is that if you are plating copper to copper, the voltage can be very, very low. Can you tell us why the voltage is not much lower than 2 volts?
So as I explained, there is a trade-off between the set voltage and off reliability. So to ensure the off reliability, we need a large, higher voltage. But you're right. We need a high voltage transistor. So the high voltage transistor occupies 70% of logic cell, our logic cell. So we need to reduce the area of the transistor, I mean selector transistor. We want to reduce to 1.8 volt. So this reduction can benefit the area. Area will be a half of logic cell. So if the operation voltage can be reduced, we can reduce the voltage. It depends on the operation voltage of the CMOS.
So as I understand you, you can reduce the voltage, but you're worried about the off state.
Yes.
And so I don't understand everything, but it seems to me the off state means you have to electroplate. It means to move the atoms away from the short circuit. And so isn't the current more important than the voltage in creating the off state?
For off state, current is not important. For on state, current is important.
Okay. Well.
Is it okay?
Any other questions?
You show the 2-terminal and 3-terminal atom switch. The 2-terminal switch had 10 to the 4th cycles endurance, and the 3-terminal has only 100 cycles.
Yes.
Is there a fundamental reason why they are different?
So for 2-terminal, we can easily monitor the on state because there is a big current jump. But to control the bridge in the 3-terminal, it's a little bit hard because we apply the gate voltage. There is no feedback. For 2-terminal device, there is a feedback. That's why. So if we control the bridge precisely, I think the cycle endurance become better.
Okay, if there are no other questions, let's thank Dr. Sakamoto one more time.
Thank you very much.